So last time we did talk about robot classification, so here's another one running around. Some key terms for y'all to know. That is actuator stroke. Who knows what an actuator is? You should have also heard about it in hydraulics pneumatics. That's exactly what an actuator is. Um, so an actuator is something that takes an energy source and turns it into mechanical movement. Okay? So with what you're thinking of with actuators, one thing you might think of is in hydraulics and pneumatics, we use pistons. Those are linear actuators. You also have things like motors and rotary actuators. Those are rotational actuators. So this actuator stroke is the total extent of the actuator movement. So in other words, the absolute ability it has to push itself out and then retract. Hard stops, you should be kind of familiar with these because they're used a lot. You have devices that stop the motion of an actuator before it reaches its full, okay, that's gonna bug me. Full stroke, not stork. Really? Okay. So device is used to stop the motion of an actuator before it reaches its full stroke. What were you asking? No, what you're looking at with something like this is, let me see if I can draw it out for you real quick. So if this is your cylinder, okay? I've got it mounted to a line, but I don't need the full stroke. Instead, I'm going to put something like a hard stop or a variable stop so that when this guy extends, he can't go past here. That's what we're talking about with this, is it's a way to stop it from fully extending and or retracting. Okay? No, what it does is basically stop it cold. I don't know if y'all know what extrusion is, where they basically push stuff into a mold to create things like plastic parts, some types of food, and things like that. Um, huh? Cast metal, things like that. So with that, you don't want to end up with a dry hopper, right? You don't want everything in there to just be pushed all the way out if you're having to be in big production batches. You understand what I'm saying? So this would hold it back from like that last inch or so that it could possibly push that would end up emptying the machine out completely. Does that make sense? It's just a way to make it stop before it's reached its full either extension or retraction. Let's say that you have this cylinder in a tight spot and you don't want it to retract completely because then it might not come back out because it'll snag on something. That's where these come in. We have stepper motors. These are DC motors that rotate in single steps due to an electrical pulse. I'll show you all one of those here in just a minute. They are actually really cool. Two of the biggest things we classify these guys as is these two, open and closed loop. And this is something y'all might want to put down as some notes, or you might want to try and find a way to memorize this, but because these are a major classification. Okay, and people get these two confused with each other all the time. Open loop and closed loop. So open loop means that the robot will receive no feedback from its environment. Okay? It is the most simple types of robots. It has permanent hard stops to make it to where it can't shift out of place. Versus something like a closed loop system, which is actually what these guys are over here. They are closed loop robots, huh? Mm-hmm. Well, these guys do receive feedback, if only from the motors that they have. A open loop robot has stepper motors, which stepper motors, they don't really care where they're at. They're just moving through the motions. These guys are a little bit different. So these guys have feedback, which makes them a closed loop system. The ones you'll be working with here in a little bit are an open loop system robot. They receive no feedback from their environment. They don't even know where their joints are. Does that make sense? By the way, that's kind of a great test question, isn't it? All right, everybody good? So basic classification, you have control systems, that's open loop or non-servo. So that is, again, whether you're using a stepper motor, which gives no feedback at all to the actual motor, to the actual robot. And then you have closed loop or servo. So these guys all over here have servo motors. In other words, I can pick up the teach pendant to any of these robots, and I can program in an exact coordinate point, and the robot will move to it. Without fail, it'll adjust all its joints in the same kind of way. Does it make sense? Versus a open loop, which, like I said, it just doesn't even know where it's at. It's totally bewildered. Okay. One thing we classify it is arm geometry. That's one of the big ones. Rectangular or rectilinear, or you can even call it Cartesian. We'll talk about what Cartesian is here in a minute. You have cylindrical. In other words, it's moving in a giant cylinder. Selective compliance robots, that's SCARA. And then you have spherical and jointed spherical. Drive power source, which one is the most common? Nope. Electrical. Electrical is the most common one there is, because electrical is run through every plant in the world. Electricity. I would not want to pay Mercedes power bill. You use pneumatics and hydraulics not so much for the robot itself as you do for the tools that it gets used with. Now, there are some that are run by pneumatics and hydraulics, yes, but at the heart of everything, you always have to have electricity. Hydraulics and pneumatics don't work without electricity. Mm-hmm. Even if you're using a generator, you're still using electricity. Hmm? Mm-hmm. So that's why I said the most common power source is electrical, because electrical is pretty much king. You can't compress anything without having the electrical. So, and electrical's in just about everything in the world. I mean, there's a few plants and manufacturing things out there in the world that don't have electricity, but quite a few, well, I'd say about 80 to 90% should have electricity somewhere, some way, somehow. versus having to buy everything you need for hydraulic or pneumatic systems, because not every plant has hydraulics or pneumatics. So the drive source are part of what we classify them as, and we classify them as what they do. Are they just a basic assembly robot? Are they a non-assembly robot? In other words, they have other purposes. A general purpose, which is what all these guys are. And then you have mobile, which, have you ever seen a bomb squad robot or the Mars rover? Those are mobile robots. Okay. They are actually able to climb around on things and discover their environment. So it is. So the little what that's actually called is an ROV. Uh, but essentially it's just an underwater robot that you can move in 3 different planes and you can explore the seabed. So I'm trying to remember what ROV stands for. Remote operated underwater vehicle. All right. So then basic classifications. So we also have path control techniques. So one of the robots you will see here is we've got this big red one in the middle of the floor over there. He's a collaborative robot. He runs 2 different ways. He runs continuous path, where you can actually take the arm and move it through every place and every movement you want it to move through. Then you have the point-to-point method, which is what all of these guys run on. Is you put in a point saying, I want you to come to this coordinates before you move to this coordinates. So you have controlled path, which we'll talk about what that is, and non-controlled path. And then we talk about intelligence level. I think we talked a little bit about this last time. But intelligence level, so this is just like your computer. The more memory you put into it, the more, if you're a big gamer, the more tools and stuff you have built into it, the easier it's run, right? To do your games. But it's also going to be more what? It'll be more expensive, right? It'll be more expensive, but and more powerful, but it's going to cost you a pretty penny versus going and getting something that basically only uses Microsoft Office. Huh? Versus a basic laptop or a very basic desktop that only run Windows Home, and you're able to do Microsoft Office on it. Big difference between the two. Okay, so the low technology tends to be cheaper and easier to fix. However, it can have its drawbacks. We'll talk more about that later. And then high technology tends to come with more expense. Okay. So here's a very simple one. This is for material handling. This particular one is a high technology because it gets sensor feedback. It's closed loop because it uses servo motors as well as other forms of feedback. It's electrically powered. It moves in a cylinder. You probably can't see it too well, but it just runs up and down. This runs in and out, and then this guy swings on a pivot. He's able to do point to point, so in other words, he's got points that are sorry about that. So he's got different points that are going to make him move around his work area to do whatever job he's being made do. Make sense? So open loop, there is no feedback. Okay, I can't say it enough because this is one of those that everybody seems to get wrong, especially on tests. With open loop, there is no feedback. With closed loop, you do have feedback, if only from the motors in the robot itself. Okay. That feedback on those robots indicates its position and its speed. How fast did it get to that point or needs to get to that point, and what position does each joint need to be in to get to that point as accurately as possible. Versus an open loop where it has no feedback, it doesn't know where it's at, what it's doing, it's just going, okay, so I'm going to move till you tell me to stop, move till you tell me to stop. These generally run on things like timers. What now? Yes. So basically what the timer is doing is say, move these 3 joints this way for 30 minutes or 30 seconds. Now, the only bad thing is so to kind of give you an idea of this. All right, hold on. So for an open loop, let's say I've got a robot that's sitting in this square right here. And I tell him, I want you to go and face this way, and then for 30 seconds, I want you to run this way. Well, it's fine and dandy as long as I find some way to bring him back to this point right here before I tell him to do that again. Why? Because he doesn't know where he started from. He doesn't know where he's going. He's just sitting there going, okay, you said move this way 30 seconds. Okay, well, you didn't tell me to move it back that way 30 seconds. You just told me to move this way. And then if you keep repeating that command, he's just going to keep going that way. Like what now? No, point to point means that you get, this is a bit of a different robot. So you got the robot arm and you tell it to come to this point right here. He will go to that point non-stop every time. And if you tell him to come over to this point afterwards, it doesn't matter what position he's in. He could be sticking straight out on that table. But he'll still go to this point, and he still will be able to go to that point, no matter where else he starts in the program. That's the difference between open loop versus closed loop, as well as point-to-point versus continuous motion. With continuous motion, you're recording what you're doing. Point-to-point, you're saying, it's kind of like driving directions, okay? Whenever you're given driving directions, it sits there and says what? Go up this road, stop. Make a left, stop. That's what point to point is. Okay? Versus you get in the car and just start driving. That's continuous. Okay? You don't know where you're going. You might not know your way back after you get yourself lost. Things like that. Does that make sense? Yep. So that's the difference between the two. So closed loop with the servo motors and point to point is able to get to each point precisely versus a open loop which has no idea. They're going to be open loop. All right, so this is a robot path. So this is a point-to-point path. So it starts at 1, it moves to 2, moves up to 3, goes to 4, cuts the corner to 5, 6, 7, 8, back. Now, if this is a point-to-point, and it would be best with a closed loop system because the closed loop is going to give me feedback and say, hey, this is the point I'm at, this is the position I moved in, and this is the speed I moved at. So it's able to give you all the nuances. versus open loop. If this was open loop, if you don't have everything down to the last detail on this as to how it's supposed to do everything, then it'll be off. You might end up starting at one, but that doesn't mean that you're going to go back to one. You could end up anywhere along that same area. That's why point to points are a little easier to deal with, because you could tell them a point and they'll go back with accuracy that would astound you. Like within 10,000ths of an inch. We're talking micrometers to nanometers. Okay? In other words, their variation is about the thickness of a human hair, if not smaller. Yeah. Okay. So with open loop, we use the robot with actuator strokes. So what do we say an actuator is again, guys? Something that moves when power is applied, essentially. So if you use fluid power, it's a pneumatic actuator. If you use hydraulic, it's a hydraulic actuator. If you use electrical, it's an electrical actuator. Jesus. But the whole point of it is that the actuator stroke is just that. All it does is take some form of energy, hydraulic, pneumatic, or electrical, and turns it into mechanical movement. Okay? Think a steam engine, right? How did they move those wheels? And they use those big old pistons or cylinders that are attached to the wheels. I know what I'm talking about? Yes, that's the old style. So with this, so we have the actuator stroke, fixed hard stops. And we'll kind of go into the other room and look at the line so we can kind of look at these a little more closely. Because that has a really great bunch of open loop robots. But fixed hard stops, basically, fixed and variable hard stops, all they're going to do, so here's my cylinder again. Huh? Mm-hmm. So what it's going to do is whenever the piston extends, and we'll just draw a block on here. When it extends, it's going to hit this hard stop. But when it retracts, I can put a hard stop here. And I can move those in order for the robot to stop sooner or stop later. Okay? But between these two hard stops is where the work will happen. Does that make sense? No, generally it's a physical stop. It's something that, kind of like a typewriter. Have you ever seen a typewriter used? Where you sit there and you press the keys, and then it hits the very end, and you have to push it back. Okay, so the reason it doesn't just come completely off that typewriter either way when you push it back or move it forward is because you have something stopping it. Does that make a little more sense? So essentially that is the principle of this. Just a way to make sure that everything stays in place and nothing kind of tries to jump ship. All right. Any questions so far? Fixed hard stops mean that they are going to be stuck in place forever and ever, amen. Variable means you can use variable hard stops allow you for adjustment. Fixed hard stops don't. Excuse me. So open loop uses stepper motors. I'll have to find one out and hunt one out here in just a minute. But essentially, when you grab a stepper motor and you start twisting the top of it, you can actually hear it click into each notch. That's all it does. Is it has the best way to draw a stepper motor. So basically, a stepper motor moves in steps. It can move in however many increments you want to put in this, but it's just like a clock, okay? Every time it gets pushed, it moves just that little bit, okay? Now, what's so great about a clock is the fact that we can set the time ourselves, right? The clock really doesn't know what time it is. It doesn't care. We have to be the ones that set it, right? With stepper motors, it's basically the same thing. All it's doing is moving in those increments. And then we use timers on this as well because it has no real feedback. We set the limit of its movement usually by time and with hard stops. Okay? Because these are things that run on stepper motors. Stepper motors, they like a clock again. It doesn't know what time it is. It just knows that it needs to keep the little hand moving, right? Make sense? Do I know? Yep. They use stepper motors. Okay. Everybody good? So then actuators. So this is the total. So an actuator stroke is the total amount that the total extent of the actuator's movement. With linear, you have hydraulic or pneumatic. There are some that are not so much. They're still actuators, but they're called something different. I can't think of the name of it right now in electrical. Uh, so when you're looking at hydraulics and pneumatics, it's what is the full retraction and full extension, okay? So if you ever taken hydraulics and pneumatics, whenever it fully extends, that's the maximum it can extend. That's the total actuator out. How much it retracts is the total actuator in, basically. All right, and then you have rotary, which is how far does it rotate? Okay. Does anybody remember the old rotary phones? You had to put your finger in the number and go and move it over. Oh Lord.
Yeah, it works. You got new modern stuff, but you've got that hooked up for no reason.
I don't even have a house phone anymore. So rotary actuators, how much rotation does it have? So here's your actuator stroke. So again, it's how far does the cylinder extend versus how far back does it retract. And these are hard stops. They can also be called, this one's got a collar on it, which they're calling a mechanical dog, which all that is just a way to catch the cylinder between the different stops. Does that make sense? And that's simply so you don't damage the gripper by trying to grab it, because those tend to be very delicate, to where if you start really beating on it, it's going to tear up. However, mechanical dog, they generally build that out of steel or aluminum, depending upon the material the customer wants. They can even make it out of 3D printed plastic for whatever they're trying to do. Huh? Well, what's the dog do? You can confine a dog, huh? It obeys commands, things like that. I mean, there's about a million and one reasons you can call something like that, okay? Kind of like, why do we call a Phillips head screwdriver a Phillips head instead of a cross head? Um, so why it's called a mechanical dog, I don't really know. It could have something to do with the fact that somebody just said, oh, let's just call it this. Or it could be similar to the fact, again, goes back to who in the world names a cross-shaped head on a screwdriver a Phillips head? I mean, we call the flat blades a flat head. Why do we call them Phillips head? I mean, yeah, except Phillips head's used universally across all brands, so it could be something like that. Moving on. So this guy has variable hard stops. The picture's not that great in it, but you can see the end stroke up here. He's got end strokes to either side and at the bottom. They have different places where they can use this guy and say, okay, I don't want you to move past here. It's sort of like, I can't think of the example I was about to use. Okay. So this guy's got several axes. He's able to move up and down. He's able to move left to right. This looks like it rotates. And that looks like about it. It might be able to extend and retract. Huh? But with something like this is a robot that's going to do a very simple job. It's going to do things like screw caps onto jars or things like that, right? In other words, we don't really need a high complex robot like these guys to screw a lid on a jar. A trained monkey can do it. Those are the kind of jobs you use low-tech robots on. If you're going to have something that welds and has to get into all these different weird positions to weld, then you want one of these guys to do that for you. Why? Because that can actually save a lot of lives. Welding tends to produce a lot of fumes to make you sick if you're in it too long. So humans climbing into pipes to weld, huh? Well, humans getting into a pipe, let's say to weld, is never good. Confined spaces plus welding do not equal a good day. But a robot doesn't care because a robot doesn't need to breathe. And they can do complex welds over and over and over again to ad nauseum so that they don't end up messing anything up. Yes, they can do it a lot quicker and with a lot more precision. That's the best thing about a robot is the fact that their precision outdoes ours a million to one. Well, they don't get it perfect every time because when you're first programming it, it's not going to be perfect. But then you also have the thing of no computer program is ever 100% perfect. What do I mean by that? Well, if you have ever had your phone crash on you and had to do a reboot on it, you know what I'm talking about. I mean, all it takes is a 1 in place of a 0 or a 0 in place of a 1. Hmm? Yeah, pretty much. I go Samsung.
Somebody cracked an iPhone open to repair. There was Samsung parts all in. Yeah, I'm not doing it. What's with the Samsung parts?
All right, so stepper motors. It rotates in precise steps, rated in the number of steps per revolution or degrees per step. So the example given here is 720 steps per revolution. So in other words, to make it go all the way around, it moves 720 times. Or you could be given it as a half degree motion per step. These use a permanent magnet rotor, and you apply voltage to different windings to make the motor step. So what it's saying is essentially this. I think this one does. Yeah, there's the animation right there, guys. So essentially this is what a stepper motor does. So do you think this thing has a chance of knowing exactly where it's at to go back to it every time? No. It's completely unaware and oblivious. Just saying. Yeah, same thing here. So open loop robot systems. So this guy essentially is just going to do his job, come down, do what he needs to do, and come back up. He's not got any feedback. He just knows when this timer runs out, you do this. Or, things like that. Yes. It can be something as a pneumatic timer, an electrical timer, something that says, okay, wait, 5 seconds and then do this. So open loop, the advantage is that it's very low cost, okay? It is very cost effective. It can give you high repeatability as long as you program it correctly and get everything dialed in. The controls tend to be very simplistic because of this. However, you have a harder time controlling the speed, so if you need things to move faster, it becomes really difficult to get it to do so, right? If you're having to change positions or change anything about it, so this thing's really good for things that are not going to change over time. So think a canning facility, you know what I'm talking about? Or someplace like Pepsi or Coca-Cola, huh? Are going to use open loop robots to do it because they don't need high yes. If it's a simple job, you go for an open loop. If it's a complex job that's going to require a lot of commands and a lot of precision, you use a closed loop. Um, if you've, I don't know how many of y'all watch How It's Made on Science Channel. You see a lot of both of these kind of robots, open loop and closed loop, because they are used heavily in manufacturing. Open loops are great if your job's not going to change. So let's say you have a toothpaste factory. How many different ways can you tube toothpaste? There's like 3 designs, right? You have the pump that just stands on the counter, you have the squeeze tube, and you might have one other type. You've never seen it? Huh? Yeah, let me. Let's see. Okay, so this is pump toothpaste. Basically, a stand on the counter, and all you gotta do is press a button, and it's not as popular as it used to be. This used to be a big thing at one point. You got it for kids and everything else. So all you do is you hit the little button, you dispense toothpaste. Yeah. So something like that, you have 2 or 3 different ways you can put toothpaste on market, right? So do I need a complex robot to make those? Or can I use something that's very simple, open loop, to put everything together? It'd be cheaper and more cost effective. Wouldn't really have to change much, right? If it's a high repeatability job, you don't need high tech. If it's something that does not change, so let's say uh, not just toothpaste, but hair products, stuff like that, where it doesn't take a lot of effort to do the job. It's a high repeatability job. Exactly. For cars, we think about Mercedes cars. Uh, for something like Mercedes cars, you need to have high intelligence because you're switching between, you might have minor differences between models that are coming off the same line. Hmm.
But yeah, you get the convertible, and all it is like a.
Yeah. Well, so that's why open loop is used in a lot of manufacturing, is because it does not require that feedback. If you're making toothbrushes, you don't require feedback. It's just going to assemble it. Basically, you're buying motors and maybe a few other things for the most simple of them. Um, I'll put you this way. Robots like these can cost in the thousands of dollars. Yep. The little yellow robot there probably cost about 20 grand. The really, yeah, you're looking at high expense versus something like an open loop robot, which is not going to cost you very much. Um, what? So as y'all saw looking at the lines over there, if you're going to have to work on the work cell, you have to have a lot of precision, because if you're even a micrometer off, you're going to end up missing what you got to do, right? So the best thing you have for these is material handling, which is moving of parts, and machine tending, which is loading, unloading, and moving things through production. That's the best way I can say that. So y'all want to we'll run through closed loop real quick. We're down to like 10 slides, so that shouldn't take too bad. So you have servo motors, which give feedback, okay? That's the difference between servo and non-servos. Non-servo does not give feedback. Servo does. It can tell what degrees it's been moved. It can tell how it was moved and where it got moved to. That's what's in all these bigger robots. Hmm. Non-servo are the ones that are the stepper motors and things like that. Okay. So this is a jointed spherical robot. So each motor in the robot arm has a servo motor, which means that it receives feedback as to where it's at any one time. Okay. So you can have a desired tool center point, can be anywhere within the works envelope. Um, you don't have to limit positions with mechanical stops, which means one less step whenever you're having to build something for this guy. The controller continuously knows the robot's position and can change drive power. Yep. No, you're going to be working singularly because we're not allowed to have people work in groups. So you're going to be working one-on-one. Or one, two. So it'll just be your name on it. Yeah, this is what we normally use when we're doing partners in labs. Huh? Mark, that is what your score would be. So advantages, they're very flexible to control with the programming control. You can change the points extremely easily. You can have a very complex set of tasks. I've seen robots that change out their own heads so they can work on different sizes of screws with assembly. Multiple program storage and execution, but it requires a large capital investment to use these. Because not only do you have to pay for the robot, you've got to pay for the cell, you have to pay for everything in the cell. It's a large capital investment to initialize whenever you get one of these. And it requires a higher skilled maintenance person to be able to keep it running. Okay. You don't want Joe Schmo grabbing hold of that controller and wrecking the robot. You want somebody that knows what they're doing when you're having to use one of these. All right. So we use these with welding. Basically the sky's the limit when you're using a closed loop system, because whatever tool you put on the end of that robot and you can teach it to use it, you can use it. Whatever application you can think of to make it do. Yeah. Heck, you could put a paintbrush at that thing's hands and put it on a track and it could paint houses. A lot of it, if it's more complex work, yes. Because you can put a camera on that sucker and you can program the camera and the robot. So I actually did this as a project for the automation company I was at, where we were sent an engine block. And we were sent pictures of, this is what you need to have it look for. This is what it would look like if it's wrong. Okay. Excuse me. So what you had to do was you had the camera mounted to the front of the robot's arm. And what it would do is it would bring that camera over into different positions around that engine block, and it would look for things like little tabs that were stuck to it and things like that. If the tab was missing, it was supposed to put a flag out and say, hey, no, this isn't right. If it saw that all the tabs, it would put them, it would say the motor's good, and it would go through. So that's what it means by inspection. A robot, if you put, like I said, you could put a head, any kind of thing you want on the end of this and make it do what you want. You can put a spring-loaded caliper on the dang thing, and it would be able to measure depth and force against different things.
Fundamentally, how, like, in this case, maybe we program it to do stuff like all that stuff. So what we did is we took a Sharpie marker, attached it to it, like, sort of places, and we had to draw stuff using the robot, the Sharpie. So
If you take the operation and programming class, we teach you how to write your name with the robot. It's a lot of fun.
It was three different, two different things you had to do. First, you manually, and then you program it to be point to point.
Mm-hmm.
And you would have to keep on doing it to try to get it as precise as you could.
Mm-hmm. classification by application, you have assembly. If you're doing some assembly, you have to have repeatability, okay? And having it to be rigid and strong, because it's going to take a lot of abuse if it's just doing assembly day in, day out, just moving things every time. It has to be kind of robust, right? Non-assembly, you have painting and coating, welding. They use these robots to apply glue inside the car so that the liner sticks. I'm sorry. And if you have it, you can use it for general purposes. So whatever you, like, again, it goes back to whatever you can think of doing with a robot. If it's a complex task, you can use one of these industrial robots and make it do, you can make these things dance. So this guy's doing spray painting. Picture looks really cruddy. This guy's doing some assembly, welding, spray finishing. Oh, so you see these tracks up under the robot right here, up under the car right here? No, those are trucks.
I'm looking, that's like more painting.
No, that's just how it looks with the picture. It's but these rails right here, I probably already told you all this, but with humans doing the spray painting, you ended up with a lot of paint on the rails. Because you ended up with a lot of drips because of overspray and things like that. In I can't remember where it is, but there's a product on the market called Fordite. Essentially, all it is paint color that is hardened over time, the lacquers, and it's basically almost like a stone. It's one of the coolest things you'll ever see. So again, this one, our automated guided vehicles, that's just a glorified Roomba. It moves left, it moves right, it moves forward, backwards. Yep. And then you have a forklift. This one's doing some welding. All right.